I'm Tyson. I'm from Western University here, one of Sharcnet's HPTCs, and I've decided to do this talk on monads. Monads are a bit of a mysterious thing you may have come across. They show up in lazy functional programming languages, specifically Haskell. They've been linked to the abstract field of mathematics known as category theory, which kind of adds to their mysticism. It's a bit of a hurdle if you want to learn Haskell to kind of wrap your heads around monads. They're required to perform I/O operations, so fairly fundamental part of the language. They were first sort of recognized in the early 90s, and since that time, with their continuous use in Haskell, they've been very successful, and now, according to Wikipedia at least, there are monad formulations available in several other languages, such as Scheme, Perl, Python, Racket, Clojure, Scala, and F#. And it sounded like they might even be formalized into the new ML standard. So that's pretty interesting. Now, if you look around on the internet for monads, you'll find everything from extremely difficult, or at least difficult from a person like my background, to understand pure mathematics, descriptions of them, to ones that are very dumbed down, attempt to sort of explain them in terms of, I mean, for example, there's ones that explain them in terms of nuclear wastes and spacesuits, which I'm not sure how useful that is. It seems like a rite of passage almost is to grasp monads and then do a tutorial on monads. So there's a huge abundance. There's even a page that collects all the tutorials on monads. So in this talk here, I guess I've been playing around with Haskell for over 12 years now. I don't know exactly how long, and I've gradually gained an appreciation for some things monads. I certainly don't understand all of it, particularly the really abstract mathematical part, the category theory. But I think I have an appreciation for and some realizations I've made over the years that I'd just like to share with you, and I think it might be insightful. Don't expect to understand everything in the talk. I'm just going to throw a lot of stuff out there, and hopefully at the end of the talk, some of the stuff will have stuck, and if that's the case, you will have hopefully come away with some insights. So basically, let's get started here. The monads are actually, originally there was just monads, but it was realized that there was a whole hierarchy associated with the monad. So at the top of our hierarchy is what they call pointed. So I guess one of the things I should say is monads can be possibly best categorized as a design pattern. So when you're writing code, you come to realize when you're writing sort of similar looking code, when maybe you're designing an object of some type and you recognize similarities between that object and another object you design. So monads capture a similarity that's seen across a wide range of objects. And these similarities actually have been broken down into 4 levels that build up to the full set of functionality known as monads. So at the bottom of this similarity list is pointed, and pointed is involved with values, basically. The next level is known as functors. And this here, it builds on pointed, so it's values, plus we bring in functions. And then the next layer is known as applicative. And it adds, for our values and our functions, we deal with products as well. And then the final layer of functionality is the monad itself. Originally, all these layers in the original formulation were just all squashed and presented as one, which is the monad. But it was realized that each of these layers had interesting items in their own right. So the monad actually lets you deal with layers or nesting if you want. And basically, as you go down this axis here, you add more functionality. The thing about adding more functionality, though, is that takes more requirements. So the amount of your objects that have this pattern decrease. So up here we have lots of things that exhibit these patterns. Lots of things have the pointed pattern. Fewer things also have the functor pattern. Even fewer things have the applicative pattern built on top of that. And finally, when we get down to the monad layer, there's an even smaller subset. So you always have this sort of tension here between lots of things, and the reason you have lots is because you don't have much requirement on them. And then as you add functionality requirements, you wind up with fewer things. I always like to think of it as down here, you have the ideal situation for the programmer's perspective. You know, these objects you have lots of functionality. Up here, you have the ideal perspective from the library writer's perspective. They don't have to provide so much functionality for their items. Anyway, so that's just a really rough overview, and we're going to fill this in now in a way that will hopefully make some more sense. You can think of this, by the way, as like if you're familiar with object-oriented languages, you might have a base class, right? And you'd have several instances of that, like say a person, and then you'd becoming more specific, like, oh, they're an employee, so not every person's an employee, so this is even more specific. And then the next layer might be a manager, so not every employee is a manager. And you can see, I mean, you're adding functionality as you go down. There's more things you can do because you become more specific, but you're slowly eliminating more and more of your general objects from meeting those requirements. So let's start with, well, actually, I'm not going to assume you're familiar with the Haskell notation, so I'm going to just start with a quick prelude into Haskell functions just to avoid confusion. And as an example of how we would define a function, let's say we're going to define an add function. So I'm going to give you the prototype first. So that's what the double colon means. So add is a function that takes two arguments, x and y, and then the little arrow means it represents a mapping. So add is a function, two values, and it returns a final value. And I'm putting in variable names, so just for the B. So it takes two arguments, an integer, and it returns an integer. And then if we're going to implement this in Haskell, we just say, okay, here's add, here's my two arguments, and add is equal to just x plus y. That's the return result. So that's the syntax. Except for why I'm breaking this out specifically is this is how you would define add in a typical language, like say Python or C. In Haskell, the functions are generally presented in a format known as curried. And in this case, what we have is we have add is a function that takes an argument, and then it stores that away, and it returns a new function that takes another argument and returns the final result. So add takes an argument, an x, and then it takes another argument, a y, and then it returns the two of them. And that might seem kind of strange, right? Why would we write this function this way? And the reason is, in Haskell, it's frequently useful. You want to provide the first argument at one point, and then the point later in the program, we want to provide the second argument. So, for example, we might do something quite simple. Say we want to say, well, the increment function is equal to the add function where we provide the first argument as 1. Now when I say increment 2, that will result in add 1, 2, which results in 1 plus 2, which results in 3. But by taking our arguments one at a time instead of in a group like this, it allows us to apply them one at a time. But I mean, mostly that's, you don't even, I mean, this second format is known as a curried function, named after Haskell curry, which Haskell language is also named after. But most of the time you don't even see it, right? So here again, up here, I would say 2. Or down here, I would say add applied to 1, and then that will return the function that takes the second argument 2 to give my result. I just know from experience this is one of the things that you don't even think about after you've used the language long enough, but it can be quite a source of confusion for somebody who has first seen it. The order of precedence on application is from the left, and the order of precedence with respect to this arrow, which indicates the type, is from the right. So we can entirely omit these brackets in this case, and we would normally just define this as this sort of thing. So add the function that takes an integer, takes another integer, and it returns an integer. X5 equals x plus 5. And then to use it, we just apply the integers 1, 2. And once everything's been applied, the computer will compute the result. Okay, so hopefully that's kind of clear. And you can play with this too, right? You can write these in Python using lambda expressions and stuff, but there's a lot of syntax involved in writing that. In Haskell, it makes it very simple to write your functions. So you just specify your arguments, and then when you use them, you can apply as many as you want. If you don't apply the full set, you get back a partially applied function, and then you can apply the remaining ones later. If you apply the full set, then it evaluates the function. But with that out of the way, let's return to the pointed class here, or the pointed structure. I'm just going to erase this here. The double slash in Haskell is a comment, so we're going to talk about pointed. And let's start by considering this. Let's consider a type. So monads are functionality associated with type constructors. So what do I mean by this? Well, let's consider creating a maybe type. So in Haskell, we'd say this is a new data type. It's maybe. It takes an existing type of some sort, and it can either be nothing, or it can be just a value of that type. So what would we actually use this maybe for? We can use it to represent partial results or failed return results. For example, if we're working with a typical type integer, we say x is an integer, then x has to be an integer. It can be 45, it can be 2 minus 1, but it's limited being an integer. With maybe, we can extend integers. We can say x is maybe an integer, and now x can be an integer, say just 5, or x can be nothing. So we can imagine a case, say we're talking about double numbers, and you could have an exception case where they try to take the sign of a negative, a number, or the arc sign of a number outside of the valid range, or the square root of a negative number, right? In these cases, by having this maybe wrapper, we can indicate a failure of result. So this would be a typical data type constructor, and what it does is it takes our existing types and we can build upon them. In particular, with maybe here, we can say go from an integer to a maybe integer. We can go from a character to a maybe character. So our entire set of types are available to use, to apply here. This is what this A means. It's an app. It's just a placeholder, and we can build new types on them. So this is actually our first design pattern, the pointed. Given a type constructor, like maybe, that takes an argument, you can actually view maybe as a type level function. So most of the functions we're used to are functions on the value level. So they take values and they return new values. Types can also be viewed that way. So maybe we'll take a type and it will return the new type, which is the entire set of the old types possibilities plus this new ability to have a empty value. And I mean, if we want to get, so this is kind of abstract, but you can actually say the type of maybe is star to star, where star is the special type that represents the type of types. So that's a technical detail, but if you didn't know that, you might find it interesting. And then the type of just, as we've said down here, is 5. So it would take a value of type A, say an integer, and return a value of that type wrapped. So a maybe integer. As we did right down here, we just changed this to y actually, just to clarify. So we see this kind of pattern commonly, where we have a type constructor, which makes new types from our existing types, so that expands the amount of things we can express in our language. And then associated with that is a value constructor. In this case, we've got it called just, and it takes the types of the original value, integers, and promotes them or gives us back types of the new value. So it's a way of we've got all our existing types, we can make new types from them, and then we can take all the values of that original type and use them in this new world of types. And that's actually the entirety of the pointed design pattern. And this is captured in the class statement, the Haskell class statement, which captures these. And we say that there's a class, and it's pointed. And for a type constructor, we'll just call it M. It has this structure if it provides a function. It goes from the original type to the type wrapped in the type constructor. Well, what would this actually look like for our maybe function? In this case, we say, well, we have an instance of this pointed class, and it's our maybe constructor. And in this case, our pure function will be a to maybe a, and the implementation would be, well, we take in our value x of type A, and we just wrap it with our just constructor and return our x. So with this, if I want to put these up here, I'll move this back up to the top. So pointed, this is the definition of pointed. Here's our data constructor, and then we say, well, actually, sorry, our type constructor may be A that makes our new maybe types from our existing types. I'll just put these in the comments up here. And this has this general correspondence, or this frequent programming pattern we see, which is given an ability to make types from new types from old types, we also have an ability to take those old values of those old types and generate values of the new type. So you can see it's not actually that exciting in a certain sense, right? This is a pretty simple concept. So here, I'll just put the functionality over in our picture here. So we have some function generically called pure, for reasons that may become apparent later, and it has the type, takes the values of the original type and turns those into values of the new type. So that's an example of how we would do it with the maybe. Now let's have a look at another data type. Say we want a list. So a list of A's will either be an empty list, or it will be an element of type A followed by the rest of the list of A's. And now we would also have this sort of thing, right? We could have an integer, and we could take that, and we could say, okay, well, with this list, we can generate a list of integers. In which case, it's either an empty list, or it is an integer followed by a list of additional integers. We could have a character, and we could take that, and we could transfer it into a list of characters. But a very natural sort of question is, well, does this have this same pointed functionality type? And the answer is yes. So if we have an integer, if we say we're talking about going from integers to lists of integers, if we have an integer, it's pretty easy to turn it into a list of integers. We could just have the singleton list, for instance. That's one with one element. So we could say instance pointed list, so list is pointed, where in this case, pure will go from A to a list of A. Pure some value x of type A will be just our list here. So the first element will be x, and then the remainder of the list will be the empty list. Now, of course, Haskell actually has proper notation for lists. I'm just using this, and it's all predefined. So I don't want to give you the idea that Haskell is a horrible programming language to write in. And they also have a built-in maybe type and stuff like that as well. I'm just defining these this way so you can see the ins and outs. And the default Haskell, this implementation is got this pointed functionality, and it's already in the class and all that. So normally you would not be doing any of this. So now that's an example of two. I'll actually just make this full screen so I won't keep jumping back and forth here. So there's an example of two data structures that exhibit this common functionality called the pointed functionality. And hopefully you can see what it's about. What it's about basically is you construct you've got your set of types here. I'll just draw an arrow down here. So here's your original set of types. Let me make that a little bigger. So in here are something like you've got your characters, you have your integers, you have your strings, you have your dates and your times and stuff. So we have a type constructor here, which can take these guys, call our type constructor M, and generate new types from them, mchar. So it could be, if M is a list, it'll be a list of characters. If M is a maybe function, it will be the original one with the option of failure. So it'll be maybe character, maybe int and stuff. And the pure function just makes the very reasonable statement that, well, if we've changed characters to maybe characters, can we actually get a hold of character values such as A and return a maybe version of that? And yes, we can. We just wrap it with this just expression. Or if we have lists of characters, is there a way to easily go from a character to a list of character? Yes, we can return the singleton. Now, very quickly, it becomes obvious that that's not the only instance. So, for example, another way, so here we've just taken one element and stuck it in there. We can easily take, instead of just generating one, we could say repeat that element twice in the list. Or in the extreme case, we could even go and say, okay, well, it's going to be x followed by more x's. So an infinite, this makes this recursive. So in this case here, I return a single x, a list with a single x, and this returns an infinite number of x's. Those are both two perfectly valid ways of taking a single value and making a list of values out of it. And of course, you have everything in between those two. The key point here, though, is when I'm creating this functionality, I don't know whether it's an integer, I don't know whether it's a character, I don't know whether it's a date, so I can't do things in here that depend on what the type of X is. I can't say, oh, I'm going to make a list of the given object +1, because +1 might not make sense. May make sense for integers, maybe makes sense for dates, probably doesn't make sense if the underlying type is a binary tree. So basically all I can do is take that value and interweave it into an existing structure. In which case is the very simplest example would be this maybe, where I just wrap and adjust. A more complex example might be this one here, where I repeat it infinitely in a list. Okay, so enough about pointed. Pointed is actually such a simple pattern that it's not actually broken out. I mean, there was an attempt to break it out, and then they figured, well, all the additional typing, you know, having to declare all our members member of this pointed, just was not worth what we were gaining for it. So it's actually been squashed into the functor layer. So let's have a look at the functor layer. And the functor layer arises very naturally, right? We had this one here. So we had M taking characters and integers, and then for each type here, so a list of integers, say we've got 1, 2, and so on, we have this pure function here, which will generate the lifted version, so just 1, just 2. So we have a way of bringing across values. You work with it a little bit, and quickly you want to bring across functions, right? So I might have a function like, if I go through this here, instead of values, I'll have a function like add. My add function from earlier. So add would be integer, integer, integer. Well, let's just stick with functions of one variables. First of all, so we have increment function, which was add 1, which adds 1 value to it. So it's an integer, say 2, and would return 3. And if I can change int to maybe int, so I go from int to maybe int, and I can take my value 2 and convert it to just 2. I'd like to take my function increment and change it from working on integers to working on maybe integers. So int, I guess, would be int. And I'd like to change that to function increment prime, which is maybe. The functionality to do that is the functor, is known as functors. So specifically, functors provide a mapping function for functions. So they'll take your prior function and they will give you a new function over listed type. So it would look like this here. Let me just focus here. We have a function. In this case, it's called fmap, or function map. And what it will do is it'll take a function. So a function is just something that takes a value and gives you another value back. And it would convert that into a function that takes the new values, the new type of values made from the previous type of values, and returns a new value. So this one here allows you to promote the values. This one here lets you promote your functions. So let's have a look at what this would look like using our class declarations. So class functor, so you have some type M, for example, list or maybe, and the associated function fmap would take a function from A to B and turn it into a function from MA to M. And this actually is why I mentioned the brackets earlier when I was talking about function definitions. We can actually realize that because the bracket associates, right, this is the same as a function that takes an a to b and then takes an m, a, and then takes m, b. So we can drop that last set of brackets, just exactly like I did when I had add plus integer, integer, integer. So we can consider that to just be integer, integer, integer. So by not distinguishing between, by applying the arguments one at a time, this takes the function and you get back a new function, and that function takes an a, and then you finally get back the b. So we can do that all in one pass. We don't have to create a bunch of lambda functions and stuff. So that's the subtlety there, and that's why I introduced the original one. So let's try and come up with an instance of this for our maybe class. Oh, yes, I missed one. Now, functor actually builds on top of pointers, so we also need this here, which just says that in order for m to be a functor, it first has to be pointed, and then it also has to provide this fmap functionality. So let's have a look. We're going to say instance. We want to say maybe is an instance of a functor, where now fmap is going to take a function from a to b, and it's going to turn it into a function from maybe a to maybe b. Now, because we don't actually know what types, we're going to write this thing, right? So fmap is going to be a function from a to b, so we'll just call it xy. And then this is the thing where Haskell returns, I can say this is equal to, and I can define a new function, or I can just take the next argument here. It's going to take a maybe a, I'll use mx to specify maybe, and then somehow it's going to spit back a maybe b. Well, the only way I can generate a b, right, I don't know what these types are, so I can't just go and create one, is if I can somehow generate it from what I'm given. So if we start looking at this, we're like, well, if I got an a, I can generate a b. That's what x and y does. And I have a maybe a. So in the special case that what I happened to got was I actually had the a, so I got something that was just x, so x being type a, then I can actually generate my b. I can say, well, okay, I'll take my function xy, I'll apply the x to it, I'll get back to y, which gives me my b. I have to return a maybe b, so I'll wrap it with just. In any other circumstances, I've always got my a to b, but if I don't have an a, I can't feed an a into a to b, which means I can't wind up with a b. So in all other circumstances where underscore just means I don't care what the argument is, I'm going to have to say that's it, I've given up. This has a nice, basically this is the sort of programming, if you're handling errors, you're going to have to do at the actual top level of your program, right? You're going to have to say, oh, okay, I've called this function, now I have to check to see if it returned an error or not, and if it did return an error, then I can't continue with my operation. I can't do the next operation, right? Like if I tried to open the file handler, I get back a file handle, I check to see if it's a valid file handle. If it's not a valid file handle, then I can't proceed with writing the file. If it is a valid file handle, then I can proceed with the next operation, but that operation might fail as well. So if you've written in a traditional language and you actually bother to check your errors as you're going along, your main program has more if statements. It's more about error handling than it is actually about the logic. So with this, one of the things that maybe does is it lets us hide all this, right? We can just write our functions here, a to b, as if we have all our values, and then we can use this fmap function to lift it in, which includes all this checking for errors. And as soon as an error occurs, then everything just falls apart, and then you just get nothing propagates through your program and until you want to do something about it. So that's one of the advantages of this thing here, is it hides a whole bunch of nasty plumbing details that we don't have to worry about. Now, yeah, so let's have a look at our list type. We say, okay, well, let's. Can we say list as a functor? Can we take a function from A to B and turn that into a function from a list of A's to a list of B? And the answer is yes, very obviously. This is a typical function. Usually they call it map, provided by many languages. So given a function A to B, and we generate a list A to list B. And what you do is if I have a list of integers and I'm told to pass a function that adds 1 to them, I just run it on each of those integers in the list, one after another. So in this case it'd be, so if we have our function xy and we have the first element of our list x followed by more x's, well then it's just going to be the list that is xy applied to the first element, and then the remainder of the list, the same operation repeated on the remainder of the list. Otherwise, with empty list, then we just get back to empty list. That's the terminating condition. There's an instance of shows that functors are list, and you'll actually see that most containers have most of this functionality in them as you go through the layers. Now, this isn't actually the end of the story here. So far, it's looking very much like these patterns just basically are these generic functions. But we actually require, and this is not enforced by the compiler, this is ensured by the programmer, that not only do they have these generic functions, but they behave in ways that are not surprising. Specifically, when there's apparently 2 ways of achieving the same result, we expect both ways to give an equivalent answer. So where this comes, for example, is say I had my list, or I had my maybe value, a maybe integer, and I was going to say, okay, well, what happens if I take fmap, I'm going to apply +1 function. So when you only partially apply an operator in Haskell, so I'm saying 1 + 2, for example, when I only specify one side, it actually generates a function behind the scenes that takes the other side. So here at fmap, I've got a function that adds 1, and I'm going to apply that across +2. So what we know from our definitions, what that's going to do is fmap's going to look inside here. It's going to say just, okay, yes, that's this one. I have the value. I'm going to apply +1 to 2, and the function I'll get back, what I'll get back is just 2 + 1. So it inserts this 2 in the missing slot there. It's actually probably simpler if I write that the other way around. But you have to ask, like, how, and just, of course, is actually the pure function, so I could write this as now, do we really believe, though, that should be any different from just applying the function right out front, right? 1 + 2. So we can take our pure values, stick it in there, stick one of our values in there, and then perform some operation on it, or we could just perform that operation on it ahead of time and then stick it in. Those seem like they should be very equivalent, and indeed that is the actual requirement we put on this. So we say that in order for it to actually be valid, we require that if I take some function xy and apply it to some pure value, that has to be the same as just, so I take some pure value, I put it, I have my pure value here, I lift it into this world of new types, and then I take the function and I lift that and apply it. That should have been the same as just having applied that function up front and then lifting the results in. So that is one of the requirements we have of this functor class. This is, I guess you'd call it a required relationship. So however it is that you define fmap and pure for your class, they have to obey this function. If they do not obey this relationship, you're going to surprise users of your thing, and more importantly, well, I mean that's very important, but you're also going to surprise the compiler, because the compiler behind the scenes knows that these relationships exist, and it'll use it to simplify your code. Sometimes it generates this code in a very programmatic way, and there's silly stuff like this gets generated, and it's like, oh well, you know, rather than doing these two operations, I can simplify it to just do this ahead of time. That this here is, we would expect to be much simpler from a compiler perspective, rather than to lift both the value and the function and then smash them together in the new world, just to do it before we even put it in. So it would prefer this one. And if that relationship does not hold, then you might get surprising results from your program. That's the one item we require to hold. And the other item we require to hold is, say I have two operations I want to apply. So I want to apply, say, x to y, and then I want to apply y to z. I could do that. I could say, okay, well, I'm going to f-map x to y. I'm going to map it across my maybe x's, and then after I'm done that, I'm going to lift my y to z function, and I'm going to lift that across the maybe y's I get out of this operation, and at the end of the day, I'll get some maybe z. I would expect that to be the same, since both of these functions came from the outside, if I just composed these in the standard mathematical functions and applied it directly across. So to make this more concrete, if I add 1 to my list and then I add 2, I would expect that to be the same as just adding 3, because I'm saying that up front. That is the other requirement that we require out of our implementations of this functor fmap function. We'll do a small example. All my examples so far have been with respect to data structures. There's another interesting type constructor in Haskell. It's called IO, and it's actually used to construct computations that return values. So we might have, say, a string is a type that could be a string. For example, an element, something that would be a string would be this, or say that. Now, we can take this type string, which is this and that, and we can create an IO string. And what this is a computation which, when run, will produce a string. Specifically, it's a computation that we ask the operating system to produce a string. A typical example of this would be getLine, which type signature is IO string, and this is a computation, so we'll ask the operating system to request a line of input from the user, and then this will come back to us in a string. So I'm going to just pop over to my running Haskell compiler here, and I can check this here. So Control-T:/T asks for the type of getLine. You can see it's IO string. I can say, okay, well, run that computation. I'll type hello there. And there you can see it completed and returned with the results. Hello there. Now, IO is a functor, which means we can map our functions across it. So we can do stuff with this. So we can say, for example, I could say hello. One of the functions Haskell has is the ++ operator, which appends to strings. Hello there. So I can say, okay, well, let's say we're going to append onto the end of it whatever string getLine computes, Tyson. So here I'm saying, okay, we're taking IO, which is IO string getLine. We're lifting up this append to string function into the IO world, and we should get a new computation back, which is still just IO. A string is a list of characters. That's where that came from. A new computation back that will get a line, and it'll add Tyson onto it, and it'll return it. So let's run that. Close that line, and I get back hello Tyson. This is an example of IO being of a more complex type here that actually represents computations. And if we have time, I'll actually go and explain how that works. It's behind, it's a state passing system behind the screens. Anyway, okay. So now let's look at our next level, which is the applicative. And the applicative adds a function. There's actually several ways you can write this, and I'm going to start with a non-traditional way. So people who have played with Haskell before may find this interesting. I'm going to describe it in terms of a pair function. And what a pair function essentially does is it allows the product type to pass through our type constructor. So given a pair, an element of this listed type of A and a listed type of B, it can squash those together and produce a single value that contains both an A and a B paired together. And you can see what's happened here is basically these brackets have moved inside the M's to the A and B. And this here, writing it this way, I'm writing it in what would be called the non-curried format. I can equally well write this as if I just delete this bracket here and this bracket here, I can take in the M and the A separately. Oh, I've got snapping on. Hold on a second. There we go. I can take in the M and the A as separate arguments. And if you think about that, that's actually because putting things together in a tuple specifies an order. There's a first argument, there's a second argument. Passing them to a function also specifies an order. There's a first argument, a second argument to the function. So those are the two equivalent ways. This is, again, getting back to that whole currying and uncurrying of functions. So I'm defining applicative in terms of this. So let's in my list here, yes. So applicative. The key functionality in applicative, say a type constructor has the applicative one. First of all, it first has to be a functor. And applicative, so long as we provide one of these pair functions, which takes an MA and B and gives back an MA combined with a B. And this actually is why we get into I/O. The Haskell is a lazy language, which means it doesn't actually evaluate a typical language, right? If I call some function, say function, I provided an X and a Y, we know that it will fully evaluate X and it will fully evaluate Y, and then it will call function with those results. In Haskell, it just binds X to whatever your expression is, and binds Y to whatever your expression is, and then it passes it into that function. And if that function happens to need to know what X is, for whatever reason inside it, then it will evaluate X. So it holds off evaluating something until it actually really needs it to proceed to do the computation. And that's why they call it lazy instead of an eager language. And that makes I/O very hard to do. And the reason is because Haskell is evaluating things when it sees there's a dependency. But a lot of I/O operations have dependencies through the operating system, so they're hidden behind the scenes. I can make a directory, and it's not at all obvious that that function has to run before my next function, which creates a file in that directory, right? That's not expressed in the program in any way. There's no directory handle coming out of the make directory call, which then goes into the create file call, so Haskell sees that dependency. It just looks like two functions, and Haskell will, evaluate them in some order if required, if at all, which is why it's so hard to do I/O programming in Haskell and other lazy languages. But this applicative pattern here explicitly says, if we're thinking of I/O, I have an I/O computation giving it an A, and I have an I/O computation giving it B, and now I've specified this by calling pair. I've specified an order, MA first and MB first, and then it can combine those into a single computation that gives me both the A and B, and it does them in that order. So it'll do A first, and then it will do B. But before we get into that, let's go back and have a look at our two examples, the maybe function. So can we make an instance of, can we make maybe an instance of applicative? Maybe follow this applicative design pattern. And the answer is yes, indeed it does. So in this case, if we have a maybe A and a maybe B, then we generate a maybe A and a B. And the answer is, well, obviously we can if we're given, if we have the underlying value of type A and we have the underlying value of type B, we can pull those out, combine them together, and stick them into underlying value of type A and B. So we can write this, so we have this X and we have just Y, so long as we're given both bits, then we can provide you with both of them together wrapped in just one JavaScript vector. Otherwise, if we're missing either one of them, then we're done. We don't know what these types are. We can't create them. There might be default values. There might not be default values. So the best we can do is say nothing. That's pretty straightforward. Similarly, with list, if we're given a list of A values and a list of B values, can we generate a list of A values paired with B values? Now that's a little more interesting. In this case, it was pretty easy because we had just one value and just one value of the other type. But here we might have 10 integers and 3 characters. Can we combine those in some way? Well, one way would be if we just said, we combine the ones we have according to their list position, and when we ran out of one of them, we just gave up. So in this case, we can say, well, if we have a value of type X and some more values of type X, and a value of a value of Y of type B, and possibly some more values of type Y, then we can at least do the first one. So we'll say, okay, well, there's your X, the first two paired together, and then we'll just, repeat again for the remaining. As soon as we run out, so one of these is nil, then, well, we'll just truncate the other one. In this case here, if we had a list, say 1, 2, 3, and A, B, we'd get back the list of 1, comma A, followed by 2, comma B, and since there was no number to pair with the C, it would just be dropped. And you recognize this if you play around with lists and stuff. This is what we typically call the zip function. It takes two lists, combines elements in the same position, and truncates on whichever one is shorter. There is another option. And if we're looking at this from a mathematical perspective, we consider this a dot product, right? You have two vectors, say each with 4 elements. We combine the two elements together in similar positions. And when we're thinking about it from a mathematical perspective, we might think, oh, well, the dot product is the inner product. There's also the outer product, which is for each element of the first list, we combine it with every element of the second list. In this case, we have an implementation of something like this. So if we have an element in the first list, then what we're going to do is we're going to take that element and we're going to combine it with all the other ones. So do we have a function as this? Yes, we can take our fmap function. Here's a function that takes x and it adds the second argument to it. We're going to apply that across the y's, and then we are going to append to the end of that list the remainder of the jobs. We'll just repeat the process on the rest of the x's. And haven't defined what this append function is. Append just appends to this, so as long as there's elements in the first list, we pull them off, and we repeat on the remaining elements. Once we're done the first list, then we just continue with the second list. All right. So this is the outer product, and that's an example of two possible implementations. Which implementation is correct? Well, they're both correct. It depends on which one you use. Which one is the default you have in Haskell? You actually have the outer product is the default, and that probably seems a little surprising, but there are some good reasons for that, which will become obvious later. And if we go back up to the functor, I realize I never specified here. It looks like I erased my, or sorry, if we go back up to the pointed ability, where we had the single x and infinite number of x's, I should mention that the single x, the single wrapping it up as a single value, is the default functionality that Haskell does for lists. Again, now we can ask the question, as with the functor level, we actually expect applicative to satisfy certain requirements. And these requirements are actually fairly natural. If we pair x with y and then pair that with z, we would expect that to be the same as pairing x with y paired with z. So it has to be insensitive to the ordering we do pairing. So here it's three elements paired. It doesn't matter if we first pair x and y and then z, or if we first pair x and then we pair that with y and z paired. And we also, of course, require, again, so if I'm going to write this, it's a little bit ugly to write, though, because I have to convert these two to the same. So I'd write it in this format here. I'd say fmap, so I'm going to normalize the format, so I'm doing these the other way around, actually. So I'm going to take my x, my y, and my z. A single slash like this just introduces a lambda, so this is a function that takes this three tuple and just normalizes it by getting rid of the grouping. So if we pair mx with the pair of my and mz, that should give the same results as pairing pair mx and y. Of course, because the brackets on the inside are going to line up normal, we're going to have to use our fmap here to normalize this one as well. That's the first sort of relationship we require. And it's a very straightforward relationship, right? It's a little noisy to write due to this necessity of stating that x, y, z grouped on the left is the same as the right. The second relationship we would require to happen. So here we're saying basically that pair is groups okay with itself. As you can imagine, we want to pair a pure value with another value. That should really be the same as just using our fmap function to do the same thing. So this gets back to the same point here, where we're saying, if there's two ways to do the same thing, they should obviously give the same thing. So if we first take the x, we stick it in our world, and then we smash them together at the pair function, that should really be just the same as saying, oh, well, start with my y's and add an x to them. And of course, that goes the other way around as well. So if you have an x, or this is a list of x's, we pair it up with a single that should be the same as specifying it directly with a math function. Yeah, so it's looking like I'm pretty much out of time, unfortunately. So I'm going to just tell you what the last layer is here. And I'm not going to have time to get into it. This functionality here allows you to do your I/O. So you can pair. So you can say, okay, when you pair things, you've specified an order which gets reflected at the I/O there. And I guess I should also mention that pair. I said I defined this in type of pair, but if you actually look inside Haskell, you're not going to find an appare function. Instead, you're going to find an apply function. A signature that looks like this. So it takes a listed function A to B and applies it to a listed value A and gives you back an MB. And now when I say listed function, you notice our fmap would generate MA to MB. This is a function that has been lifted inside the item. And it's pretty simple to write this function in terms of our existing functions. We just take basically we take our MAB and we join it with our MA with our pairing function. So we pair MAB with MA. And what this will give us is this will give us a result like this. We'll have A to B with A. And then what we do is we just use fmap to push a function in there, and this function just simply takes, it's got the AB and it's got the A, so it just applies the AB to the A. And then that would convert that into an MB. That's the standard function you will see defined in Haskell. And that is entirely equivalent. Given it, you can also write pair if you're going the other way. So if you do want to pair a function in Haskell, you can write it as this. And so given an MA and an MB, use fmap to combine the MAs with the So let me just tell you the last layer here. The last layer provides a join functionality. And the join functionality lets you join together nested layers. So in this case, we saw we had separate layers and then we joined them into one. In this case, we have a nested layer and we join those into one layer. And you run into this problem immediately if you try and use the applicative. It's great as long as for say I/O, it's great as long as your structure of your program is fixed. So if I want to say, oh, I want to read the line and then I want to read another line and then I want to write someone's name to the output, that's great. I can say do this operation, do this operation, do this operation. But as soon as I want to have the structure of my program vary, so I want to read a line, and then depending on what that line is, I want to do one thing or another thing, you can't actually express that with the pair operation. And when you try and express it, you'll wind up with two layers. So you'll have your initial result, so you'll get your initial result back in, so IO string, and then you're going to try to do something on that, so you map your function in there that makes its decision. And then it's going to say do something else, so then you wind up with another level of I/O nested inside your I/O. So you need some way to say, okay, I want to evaluate this confusion, I want to evaluate the outer layer, and then I want to evaluate the inner layer. I want to squash these together, and that's what the join functionality does. And then once you have this full set of functionality, you actually have all you need to specify I/O in Haskell. And it's also, as you've seen, the set of functionality, though, is not just limited to I/O. It applies to most containers, such as maybe in lists. It applies to a whole bunch of more complicated things we can pass around. There's something called the reader monads. So these are functions that take an environment and compute a new value. It applies to something called a state monad, a function that behind the scene takes a new state, computes a value, and also passes back a new state. So you can have a state threaded through your program. You can have continuation passing monads. So that's a function that actually doesn't return. Instead, it takes another function that tells it what to continue with. So there's a whole wide range of items, and I/O is just scratching the surface, that follow these patterns, and that's why they've become so useful. Most other languages are eager languages, so they don't have the I/O sequencing problem of Haskell, but the reason we're seeing this monad formulation show up in other languages is because of these other things which also follow this same pattern. So I guess that was all I had to say. Well, I had a lot more to say about actual monads and some examples, but we'll open it up to some questions now.